Yeah, we have a few different topics for today that we can kind of, see what we get time for. Um, the first one that I kind of shared was discussing a potential compositional paper that we might kind of choose to work on. And so that hasn't been decided yet. There's kind of different, high level strategic arguments we can make for pursuing a paper or not doing that. Obviously, there's a fair amount of overhead with that, and that's effort that could go into something else. But just things like furthering the capabilities, and then you could argue, okay, well, how much impact does a new paper have versus just increasing Monty's features and things like that. But I think in order to have an informed decision about that, it's useful to think about, okay, well, what would that paper even look like if we were going to do it? And then even if we don't, if we decide not to do a paper, that could still inform kind of experiments that we want to do to kind of convince ourselves that compositionality is working like we're hoping, even if we don't actually turn that into a submission. It could be a blog post, it could be a white paper. There's kind of lots of options.
Yeah, it could also
Um,
be like several smaller conference submissions, something like that.
right. Yeah, so there's lots of kind of flexibility there. So yeah, one thing was just to kind of discuss what measures we would look at and what kind of some of the figures might look like. And yeah, I'd say a lot of this builds on kind of, if you guys remember back in September when we were talking about first developing the compositional benchmark, a lot of the kind of related concepts came up then. Um, but yeah, so as a starting point, I've been kind of just writing ideas in this document, but it's rather long-winded. And then yeah, Vivian was putting some nice kind of summary points here, and then I've started drawing out kind of what the actual figures might look like. Um, I don't know if yeah, Vivian, I don't know if you want to start with this, and then we could look at these figures. Might be a good way of doing it.
Yeah, I guess, yeah, I can briefly go over it. Mine is not really a concrete proposal. It's more maybe a
Yeah,
high-level
I guess
planning,
like kind of a
but
high level reminder or
yeah,
yeah,
like of what we want to look for and what we want to
right.
think about. So, yeah, I try to first collect some ideas, like the main benefits that we expect to get from hierarchy. And so those are kind of
Oh,
the
sorry.
high-level things we'd want to be showing in one way or another. And so those are faster learning since we don't have to relearn child objects. If we see a new arrangement of child objects in a parent object or one child object, like the logo is contained on many different types of objects, we don't have to keep relearning the logo on all of the objects. We learn the model of the logo once and then assign its ID to a bunch of different objects. Faster inference for one, because higher level learning modules will get more unique features. So the logo ID will appear on, oh, well, uh, yes, that's a very good thing. Um, the logo ID will appear on way fewer objects than light blue, for example, or slightly curved or flat surface. So the kind of features that come into the high level learning modules will be much more distinguishing of the object, which speeds up inference. Plus, top-down connections would make inference of the lower level learning modules faster. Basically, if the higher level module knows the scene that we're on, like I'm on the mug with the logo, and now I'm moving from the logo to the mug, it can directly tell the lower level learning module to change what it thinks it's sensing, and the lower model doesn't have to do any inference for this information to update what it predicts to sense next. Um, More information, efficient information storage and scalability. So yeah, it kind of relates to the faster learning as well. Basically, we often get the question of like how scalable is Monty? What does it scale linearly with the number of objects? And basically, if we can decompose objects into sub-objects and then arbitrarily recombine them again into high-level arrangements of parent objects, that makes it much more efficient with the amount of information that needs to be stored. Like I mentioned before, we don't have to store the details of the logo in every object that contains the logo, we store the details once, and then objects that contain the logo just associated with that model ID. Then more abstract models and better generalization. So that kind of relates to the issue we saw when we tried to apply Monty to the omniglot dataset. For example, that right now we always just look at the low-level morphology of objects, but if we have hierarchy, we can look at the kind of higher-level morphology of object parts. So although the individual strokes might be slightly different and slightly differently spaced, the kind of high-level rough arrangement of two strokes or three strokes in a letter is still similar. And so the child objects might have slight variations, but then the high-level arrangement is more similar and it's easier to generalize. Recognizing child objects on unknown parent objects. So you might see a set dinner table and you recognize the cup, even though you've never seen that specific arrangement of cup, plate, fork, and knife. And distinguishing a variety of arrangements of the same child objects. So it's, yeah, not just a bag of features where anything that has cup, plate, and knife are the same thing, but it matters how they are arranged. Or like where we have three strokes, we have three strokes in a letter that can express many different letters, but the child objects are still the same. Does that make sense? Are there any kind of high-level benefits that I missed that we would expect?
No, I think maybe one is maybe not the biggest one, but what I talk about down here is like yeah, that compositional models could be useful for policies, basically make better model-based policies as well. Because we can kind of look, for example, with the hypothesis testing policy, we can look at the difference in object ID space to inform where to move.
Yeah.
And then
Would that mean you can get rid of kind of the overlay comparison that you were doing to figure out the next move? Is that why it's better?
well, at least for now, we would still do that. But the point is, it would do it in it could do it in different spaces that are better. So as in, like, let's say you're trying to compare TBP mug versus Numenta mug. Though they have the same kind of morphology, so that's not going to tell you where to go on them. You could maybe do the comparison in like color space and say like, oh, in my learned model of the Numenta mug, the colors at these nodes are very different from my learned model in the TBP mug. But the reality is like that's not as robust a signal because yeah, basically it doesn't depend on the shape of the logo and everything like that. Like you could think of a lot of instances where that would fail. But if you actually have a representation of like, oh no, there's this logo in this one and there's this other logo in the other one, it's like, oh, those are two totally different objects. So I'm going to move to where I expect two different objects depending on the parent object.
That makes sense. Thank you.
Yeah, no worries. And yeah, this is something where like it would already work with just kind of naively storing object ID as like as a unique integer or whatever. But you could imagine if at some point we have representations of kind of object ID where there's like some semantic similarity, if they share something, then you could also leverage that. So like, I don't know, the head of a screwdriver is more different. It's further in kind of representational space than the head of a fork and then the head of a spoon. And so depending on what you're trying to kind of recognize, that might be useful information.
Can you leave
Yeah,
that?
I added that.
Can you leave the
Oh, hey,
list up
Jeff.
there? Yeah, I'm sorry. I joined late and joined in the middle of this.
Yeah, no worries. Do you want just like a high level context for the discussion, or are you happy?
Well, I assumed that someone like Vivian has decided to talk about benefits of a hierarchy. So
Well,
is there more,
but
is there
I
more
guess
context
the
than
reason
that?
is, yeah, I guess the reason is we were just talking about whether kind of over the next half year we want to do another like a new paper, this time on the benefits of compositionality. And so I was just saying kind of before you joined, like you could make different arguments for or against that. You know, obviously that could have benefits in terms of generating interest and,
Okay,
you know,
so is
but
this this
but we could
little
also,
figure's labeled benefits of hierarchy. Are we really talking about benefits of hierarchy or benefits of compositionality?
I guess compositionality might be a,
All right, because that's a more narrow topic. So I was like, oh yeah, there's a bunch of stuff that's not there.
right.
So, okay, that confused me. Right, so that's the good
So-
context.
But yeah, the
But yeah,
high
but so
level
now
question we're talking about is whether we should write a paper on the benefits of compositionality, and and to determine that answer, kind of what would we want to show in such a paper?
You know, it doesn't strike me as that's a terribly exciting topic. I mean, compositional structure is well known. I imagine many people would be able to, they look at some of these ideas and say, oh yeah, of course, you know, those are obvious things, even if they weren't obvious, but they might say that. I guess it doesn't, at first blush, I say, oh, that's not terribly exciting. Like, does that demonstrate our work is really groundbreaking and unique?
Yeah, and
I-
so I think that's kind of what we want to determine. So one of
Yeah,
the
kind of
big questions I
enumerate the,
put at the bottom here is like, what is an intuitive test condition that clearly shows the benefits of Monty with hierarchy? A problem that's easy to understand but not straightforward to solve with deep learning. And yeah, I think if we can't think of a simple demonstration that's impressive when people look at it and easy to understand why this is cool, then it's probably not worth it to write another
right.
paper. But
Right,
yeah,
and then also like,
there's
what's the existing literature on compositionality? You know, like
Yeah.
how, you know, I mean, I know we're doing unique stuff in the sense we're mapping onto Brain and Monty architecture, but the ideas
Right.
of compositionality, the benefits of compositionality, are these new ideas? You know, they're sort of
It's hard to pinpoint. Yeah. So, I mean, compositionality is for sure recognized as important to intelligence. And, but the way it's generally approached in kind of deep learning and stuff is quite different, both in terms of how it's implemented and how it's measured. So that's one of the other challenges is like, if we were to compare it to deep learning methods, you know, would we want to, and how would we?
But you know,
So I think the idea here is to kind of spend, you know, a few days a week, just kind of looking at, if we were to do this, what would it look like? The worst
Right.
case is we decide, okay, we're not going to do this, but maybe we've thought about some experiments which would be interesting just to convince ourselves that compositionality is working the way we have hoped.
Well, that's one thing.
And
Obviously, we have to do
yeah,
that, right? We have to implement our theories. It's important to have it in the system. Monty
right.
has to do this. I'm just thinking. I'm a casual observer of deep learning. I'm not into it deeply. I'm a casual observer of it, and compositionality doesn't seem to rise to any of the topics that I hear or read about in deep learning.
Yeah,
You know,
it's more of a kind of research
right,
topic, but
right.
Yeah.
and generally they look at things like you know, kind of disentangled representations is often a term used, so that, you know,
Right.
the classic data set for evaluating this is this one called CLEVR, where it's like these different objects of kind of different materials and shapes, and
Yeah.
then if you have kind of a compositional object-centric representation, then you can kind of go in and you could, for example, change this object to be teal, and then in the newly generated image, just this object would be teal, or you could delete an object.
Right. Okay. All right. But
So you can see how it's kind of, it's related, but it's also quite different. Like this, I don't know, it doesn't necessarily get into the what we're talking
ask
about,
ourselves,
like
why, you know,
parent-child.
why are we writing a paper? None
Yeah,
of us are academics. We're not trying to get tenure here.
right.
You know, we're trying to advance our platform first and foremost. And if writing a paper gets people excited about our platform and gets people to pay attention to it, that's good. Compositionality doesn't strike me as very exciting, just being honest with you. It's like, oh yeah, we have to do it. We have to really solve it all. It doesn't like, wow, it's amazing. You know, I'd rather, I mean, if we had a paper studying something really unique about action policies and problem solving and robotics or something, that would be far more valuable. So
yeah, so
I'm
I think
just,
that's kind of the main question is, could we demonstrate something in a paper that would be exciting? And so one of the other questions I wrote down was like, do we need to compare to deep learning? And right now I tend towards probably we shouldn't, and instead either use a task that deep learning doesn't solve, like where it's clearly an unsolved task, and that's why it's exciting that Monty can do it. Or yeah, just focus on the advantage of Monty without hierarchy, and advantage of the systems improvement. But I think it's still worth thinking about if there's a cool way to demo this new capability, because I mean, we are spending a lot of time on adding it to Monty. So even just for ourselves to think about, all right, why are we adding this? What new applications and capabilities does this unlock? What
Right.
Why should people be excited about Monty now being able to model compositional objects?
Okay, so
And
a
even
while
if it
back.
isn't a paper, again, it could just be like a blog post or something,
All
like
right,
something
so
that's a much lower lift, but still
so
get
yeah,
some
so
interest.
we explored compositionality in terms of logos on mugs and static objects. Lately before the holiday break, I was talking and we were discussing issues about forming temporary objects in the hippocampus. You're constantly attending the objects, building temporary models. Those models are all hierarchical. They're all compositional models. Even if they're temporary models, they're compositional models. I mean, it's sort of inherent to the whole system that every time you attend to something, you're building a compositional structure. And so, I could say like, all right, well, logos and mugs, we've already written about that a couple of times, and that's not very exciting. If I would say, oh, I could do a thing about compositionality, about dynamically learning new environments, and building temporary compositional structures as you're going around to tend to different things in the world. Um, that seems to be a bit more closer to like robotics and towards intelligence. And I mean, there's other ways. Well, I guess I'm saying is the compositionality piece is sort of inherent to almost everything that's going to go forward. And so I don't know. I just feel like I'm gonna demonstrate.
Yeah, well,
I
I
would
mean, and
demonstrate
I
on
think
something.
partly that relates. I feel like that relates kind of to what data set we would look at. And yeah, I think we'd want to look at. I mean, I think if we wanted to get it published, we'd have to look at multiple data sets. But I think that would also make it compelling. And yeah,
Yeah,
um, so some of the ones we've looked at before are this kind of omniglot one you may remember, of kind of
yeah,
these
I remember
different
that. Yeah,
characters from different alphabets around the world. Obviously, we have our
yeah,
kind of logos on shapes, which we could expand and make more interesting, different textures on many different shapes and things like that. And then we have kind of more like what you just described, this kind of like scene level representation. One which we had implemented was that kind of different dinner tables, kind of arrangements, and things like that. But I mean, one of the things that I think is kind of cool about this, again, it might be more interesting to kind of, hardcore researchers rather than the general public. But this one is 2D on 2D composition. This one's 3D in 3D composition, and this one's 2D on 3D. And so it'd be kind of interesting showing all those kind of the flexibility to work in all of those spaces.
right,
Um,
right.
and
Well, again, I think this
yeah,
comes back to, I think, what is the goal in writing this? And you said it, I said it. It's like this is more attractive to a researcher, and it's harder to get a lot of attention to a project when you're dealing with topics that are really only researchers understand and appreciate. Um,
yeah,
that's
yeah. Because
that's my take. Doing
right,
a paper is a
I think
lot of
you're right.
work.
Yeah,
It's a lot
no,
of
I think you're
work,
right.
and you're gonna spend a lot of time on this.
Yeah, yeah,
Um, I just feel
yeah.
like, boy,
Like
if I was, well, if we're going to do another paper, let's do something. Let's pick a topic we think would be exciting and figure that topic out, and then make the paper.
yeah,
That's a,
yeah. Because
um,
I think like a blockbuster result in this case would be kind of sort of solving omniglot, which, at least as far as I'm aware, um, remains an open challenge because
yeah, but
that's but
even that,
yeah, well,
imagine
exactly.
the, imagine
Yeah,
the headline.
it's not the most because I mean, firstly, it looks like a really simple data set again to the average person, or
Yeah,
like compared to what ChatGPT and Gemini and all these models are doing. Whereas I think you're right. I think something with kind of more action policies or dynamic objects yeah,
Try to
would
imagine,
stir
try to
more
imagine
excitement.
a front page headline on the BBC News page. Okay, so one is the 1,000 Brains Project solves the omelet data set. That's not very exciting. No one's going to want to read that. That's never going to make the front page. But you could
Right.
have fundamental problem in robot learning has been solved. Something like that. That's okay. What is that?
Yeah.
It's not the omelet data set. You could say, hey, look, these things have to do continuous learning. They're building these models continuously as they observe the world, attending to things, and these models happen to be compositional. That's the way the world is structured, and so we can build temporary compositional models, and even a white paper showing the spectrum of things like logos on coffee cups to placemats on a table to the objects in an intersection or on a busy street. Even just uniting those concepts, that's an interesting idea. Most people wouldn't understand that those are all the same.
Yeah.
Something like that. I don't know if that's a paper or if it's a white paper.
Yeah.
Yeah,
And
I
I
think
think that's kind of the
I
direction
think
we were leading.
yeah,
But
I mean,
yeah.
I think we should publish something about compositionality, even if it's not in a journal, even if it's more of a blog post or a preprint or something. But I mean, we are going to run these experiments internally anyways to make sure the system works the way we expect it to work. And I think it is quite a significant conceptual advance. So I think it will be difficult
Well,
to
can I ask you,
skip it.
where's the conceptual advance? I mean, I'm not disagreeing with you, but I want to know what you think is a conceptual advance.
I think I mean we
Or a
describe it in the
capabilities
handwriting
advance.
paper, but I think from the AI community side, it would be hard to write another paper without having a place where this part of it is explained, of how object IDs become features on other objects.
So you think most AI researchers would find that surprising, or
No, I think it's
It
more of a
would be
capabilities advance. It's like, I mean, yeah, we're definitely proposing how, I would argue the way we're proposing to use compositionality is different, but yeah, it would be more kind of just saying like, look, this is what we can achieve, which is very different from what you could with other
right?
approaches.
Well, again, right. Again, okay. I mean, look, I was kind of uncertain when we worked on the first paper, the capabilities paper, and it turned out great. I don't think it significantly catapulted our organization into the
No,
front
that's the
page
other thing
news.
though. I mean, I agree. Like, even though, I think we made a strong paper, it doesn't, it's hard to kind of make a splash. And again, like, is our time better spent just creating more features, so that, and also
Right,
to the whole incubator thing, like the more capabilities there are, the more
right.
people can build useful demos.
Well, let's just back to Vivian's point. I mean, we've got to do some of the stuff anyway, right? We have to test
Right,
this. We have to prove it, but it's a huge another step to make a paper out of it. At least that always feels like that way to me. Just all this stuff and reviews and figuring out all these details or all these references.
right,
Something it's somewhat helpful, but I think the reward or the benefits aren't worth the extra effort, and often. And
right,
so again, we should do all this stuff, but in terms of writing a paper, and then white papers are easy to do, because you don't have to go through that whole rigmarole. But in terms of like moving the needle significantly in the machine learning community, I think we're so far in the weeds compared to all the noise about deep learning these days that it's hard to imagine a paper like this would really make a difference. Maybe historically people look back and say, "Oh, look, they did all this stuff. It all worked amazing." And blah blah. But at the moment, it's like I don't know, people writing
yeah,
about AI taking over the world and destroying the world's economy and all this stuff. And we solved the omelet data set. That's what, okay.
right. Yeah,
That
so
doesn't
I
diminish.
think we're all on the same page with that. So then maybe but we can then kind of just look at some of those like concrete figures that we might look at, that we might develop, which again doesn't need to be in the context of a published paper, but just like
Right.
these are the kind of results which over maybe the next 3 to 6 months would be nice to generate.
Right. And
Um,
before you go there, I doubt you're going to have this and that, but
yeah,
I would challenge you to think if you can do one where it's a more dynamic, fast learning, instantaneous compositional structure, the kind of things we've been talking about the hippocampus doing, adding that into the list. I think that's pretty exciting. It's a pretty interesting idea.
I mean,
That
I think it's basically what Monty does by default right now, because it learns everything instantaneously.
Right. But we don't want to learn permanently, right? We want to learn temporary arrangements. That's the key.
Yeah.
It's like it's not that it's more like this idea that we go around our lives every day. We're just constantly looking at attending to things and constantly building these very temporary models. Where did I leave my glasses? Where's my car left last time I saw it? There was a person over there who was tying their shoes. I mean, I don't know. It's just like this. To me, this was a revelation, sort of realizing that my life is spent 90% of my intellectual activity is building these temporary models. They're all built on static or pre-learned models, but so they're all there in the background recognizing things. But most of what we think about as our experiential world is these building these temporary models. So I'm just maybe just think about that a little bit, like how it's not like just fast learning. It's like, how do we take advantage? Maybe it requires action
Yeah,
policies.
I think
How do we
it would need to be like a specific task or something that kind of benefits from that temporary
Yeah.
nature.
Well, see,
Like looking
here's
at
some,
things like efficiency. But I mean, there's definitely settings you could imagine. But yeah,
one,
it's not
one
something
way
we
to
have at
do
the
it.
moment.
I know, but one way we could approach this is flip it around backwards and say, I want to write this ideal paper, which shows how we have these existing pre-learned models. We have these temporary things. We're constantly building models temporarily with our environment, and those are going to be essential for any kind of intelligent behavior. You can't work in the world unless you know where you put the tool and where the last thing was, and so on. And so, if somehow we could write a paper that shows that we can apply action policies to both, these more permanent models and these real temporary models, and it's all compositional, and the world is compositional, and blah blah blah. I mean, I don't know what that is, but that would be an exciting paper. Right? It's
Yeah,
like
I guess one
solving
interesting thing is I feel like if you compare it to the rest of the literature, actually these temporary models is where most people have started, because that's really what so much robotics is about, is like, okay, where are these pick and mix objects in a scene? And
yeah.
I feel like robotics started there, and evolution kind of started there, because that's the key, that's the core thing you need, is to know kind of where you are, where other
But
things
you
are in an
also,
environment.
but
But what
okay,
makes TBT exciting is saying, okay, actually no, all of our representations are compositional, all of
right,
our
right,
representations are structured, um,
right.
not just these temporary ones of where things are in an environment.
Right. The whole thing is built this way. And there's a somewhat of fluidity between what's temporary and what's permanent. Because temporary things can become permanent. I don't know. All I'm trying to do is try and imagine an exciting article, an exciting paper, one that you'd say, like, whatever you think it is, but it really ought to be exciting. It ought to be like, wow, people are going to go, that's amazing. And then ask ourselves, what pieces are we missing to write that paper? And maybe we can then make that as a target or something like that. Anyway, it's just a thought. But
Yeah, no, I mean, that's kind of basically what we want to do right now. And
right.
So.
Maybe you've already gone beyond it, but writing a paper, a journal paper on compositionality is, maybe you've already decided that's not the best use of our time, but it didn't strike me as like exciting.
Yeah, but that's useful feedback, because I don't know, it would have been like if you had come into this meeting and said, oh my gosh, yes, definitely, I've been waiting for you guys to start working on one or something, then that would have been interesting to know. So yeah, I think we were already kind of on the fence. So yeah, it's useful to hear that.
Maybe as we go along, we got to implement it, right? And we got to test it. We got to do all these things. Maybe as you go along, you say, hey, this is a cool result. And
Right.
even maybe just a small one,
Yeah. Or again, I mean, like posting a preprint isn't that much effort. It's the constraining it to a journal's requirements and going through the review process.
Several
and also
neuroscientists
the conference submissions would be lower effort too, like several smaller conference submissions.
I mean, you could do a simple paper. You might get more results out of like a simple thing academics like solving the omni-got data set. That would be the entire point of the paper. It's very narrow, it's focused. You're going to get less, I've had several researchers over the years, neuroscientists, warn me that don't try to do big papers. It's impossible to get them published, and people don't pay attention to me. Much better doing lots of little ones. I don't know if that's true or not, but I kind of experienced that myself. So my point is that going along the way, you might be able to peel off a simpler paper that is easier to do and less comprehensive, and yet still get some of the points across.
Right. Cool. So yeah, so I guess then in terms of what kind of plots could be useful to kind of generate over the coming months for whatever purpose we decide on. Yeah, this is just a rough sketch of some of these, but imagine it was in a paper. One way to kind of structure it would be figure one, something like, compositional models reduce prediction error. And this is just to kind of build an intuition for what compositional models are, where they're kind of interesting, where obviously you'd have visualizations to go with this, but in terms of like actual kind of plot results, if you look at kind of this stepwise prediction error over the steps of an episode, and this agent is looking at the mug with logo. This is one you may recognize this from some of our earlier discussions, where kind of as we're on the mug, we kind of gain confidence about where we are on it until we have this very good hypothesis, and then that's kind of our best hypothesis, and that one's doing great predictions, and so we have this low prediction error, and then we move to the logo, and up until this point, the high-level learning module has no way of knowing whether it's the mug with the logo or not, so it's a bit surprised when it sees the logo. Which is this kind of spike here, but then it says, okay, this is, now I know I'm on the mug with the logo. And then when you move back to the mug, this higher level learning module that knows we're on the mug with the logo, because it's learned these associations of the logo on the mug with logo and the mug with the mug with logo, it can basically tell us in the lower level learning module where we should be, and therefore kind of give us this low prediction error. The alternative to this is if you have kind of a non-compositional model where you only know about mugs and logos, then every time you move on to one of these objects from the other one, you're going to be surprised and basically have to re-infer what you are looking at.
This will basically be the plot we want to get once we add top-down connections.
Exactly, yeah. But then a counter to this would be, okay, well, what if I just learned a flat model? So I described this as a non-compositional model because this learning module only knows about mugs and logos. But if you have a learning module that spends lots of time and it learns logo on mug as like a single kind of just like a single object, it would actually still get low prediction error once it's recognized that it's on the mug with logo as it moves between these. Because in its model, it knows where the logo is. It doesn't understand that that's a logo. It doesn't understand it as an object. Right, but in terms of sensory predictions, it would still get low error. So then to kind of continue the story, the reason you don't want to just do that and learn everything with flat models is basically because the compositional models generalize much more rapidly and much more efficiently. And so one way we could kind of explore that is looking at two kind of independent variables. One is sort of how much time a Monty system has to kind of learn the models that are given to it. And then, so that's what's on the left. I'll get to this one later. And then what we're looking at is a kind of the mean prediction error at inference, and then inference accuracy, maybe in a time constrained way. And so here you want higher is better as you spend more time, and here you want lower is better as you spend more time. And what we would expect is that with the compositional models, basically as you spend a bit more time, very quickly, you can reuse those child representations, as Vivian was talking about up here, to basically make good predictions, as you also kind of see here. So you get low prediction error, good accuracy, and you don't need to spend ages learning everything. versus the flat Monty model does poorly here. And then another kind of dimension to look at this is how your kind of parameter budget, like how many points in your model have you expended to learn these representations in order to perform at inference time. And so looking at the same measurements, kind of mean prediction error and inference accuracy, you'd see kind of a similar trend that the compositional model scales much better as a function of these kind of how many points you allow it to learn versus this kind of flat model. Does that make sense?
Yeah, makes sense.
And then a kind of third figure, but if this worked, this could almost be the second figure, because as I was saying, like I feel like this would be the blockbuster result if we got it working, is that composition models should also generalize better. And this is something that I remember, Vivian, you made some nice visualizations at some point. I couldn't find those, but so I just kind of recreated as close as I could from memory. But in Omniglot, I think this is technically, I think when we first explored it, it's technically a Korean character, but it also kind of looks like a Roman letter H. But anyways, if you imagine, again, we're comparing to Monty learning kind of flat models, or we're learning compositional models, and we get a novel H, this thing that's presented to us. Depending on how we kind of set the parameters for a sort of tolerance as we like move in our model space and try and match to this other model, basically, if we set them kind of strictly, which you'll understand why we would want to do that later, you know, to have a kind of sensible tolerance, it doesn't take much for variations in this kind of just natural variations in how letters appear to cause this model to fail to recognize that this is the same thing. So, you know, this says, oh, it's not a H, so generalization failure. Whereas with the compositional model, we can, at least the prediction is kind of, well, okay, let me actually then get to this one first, and then I'll go back to the compositional model. So then you might say, okay, well, let's just set the tolerances really, really wide, and then it'll still say, oh yeah, this is a H. But as you kind of set the tolerances more loosely, in a kind of more relaxed way, then suddenly, you know, sort of nonsense inputs that shouldn't be recognized as this letter or whatever the object happens to be, will kind of be recognized as such. So then in this case, the same model, now we're deciding to use relaxed matching. It says, oh, actually, this is a H. So that's a failure. But the idea is, which we haven't demonstrated yet, but is that with a compositional model, we could find kind of a happy balance, because within each, we can kind of have tolerance within a child object while still being constrained by the actual spatial arrangement of the kind of sub features. And this is kind of, I guess, showing that intuition. You can imagine quantitatively, we might look at, you know, accuracy, the flat model versus the compositional, we'd be better. And then we could kind of drill down into that and maybe do something where, for example, we look at sort of the correlation of accuracy on these kinds of objects versus accuracy, kind of classification or misclassification, you could even say, on nonsense inputs. And basically, as you kind of ramp up this quote unquote accuracy on nonsense objects by, say, increasing the tolerance, as you increase the tolerance in order to gain accuracy on real objects, that gives you quote unquote accuracy on nonsense objects, which is not what you want. This is basically becoming a bag of features model.
I mean, I don't think we even have to add nonsense objects. If we increase the tolerances, it will just generally start confusing letters with each other.
It's possible, right? Right. Yeah, eventually it will. Yeah, this is more, I guess, it could just be interesting kind of from a scientific point of view, because it kind of, it just ties into like the importance of shape and just kind of highlighting that Monty relies on shape. But I agree, yeah. Eventually, the tolerance would just naturally bleed over into the accuracy dropping.
You mentioned this would be one of the most significant results. I would have thought that the memory usage and training time would be the most advantageous component. Like, You can't learn a flat world. Impossible, right?
Yeah, right.
So
I mean, I
it
think
be-
it's the least practical bottleneck we have right now with Monty. I mean, Monty is already so efficient in learning, both in the amount of computations it needs and the parameters it needs, that it's not really a bottleneck at the moment. But not being able to generalize to different versions of the character without starting to confuse it with other characters is like a significant limitation right now. So like just if you think about what you can use Monty for today, like the training isn't really a bottleneck. We train like once every half year, and if it gets a bit faster, it doesn't matter that much. And if it stores a few more points, it doesn't matter that much. But yeah, as you
well,
scale the system, of course, that becomes a much more
right.
important
I mean,
point.
that we're dealing with, the old data set, it's like, but the world is really complex. And, just look around your room right now and imagine saying, oh, I got to learn all this as a flat model. It's just not possible.
Yeah, I just
Uh,
mean you won't really see the effect until we actually scale the system to learn like
right,
really
right.
complex environments and
Okay,
have a lot
well,
of learning
so
modules.
right, but so I mean that's where the real amazing part comes. So um
Yeah, I guess the other thing is just in terms of kind of convincing people to use Monty. I mean, kind of like Vivian said, like it's already quite efficient, but I think the main concern, or one of the main concerns people might have is like, okay, well, how robust is this? Like, can I use it on other data sets and things? And as mentioned, like Omniglot is actually it's a real machine learning data set that's really challenging. And so if we and it very specifically looks at kind of generalization to these novel instances of characters, which
right.
we haven't we've kind of explored that where we add noise and things like that. But
Well, let's just step back to
yeah,
something you said a second ago. Like we want people to use Monty. Do we want people to use Monty to do research? Do we want people to use Monty to build, products
I think
and
we I mean, we
businesses?
want them to build products, but I think what they would say is like, okay, well, what if my tomato can looks slightly different in my pick and mix or whatever.
Well, okay, but then we'd have to really get into like, oh, we're doing pick and mix stuff, and maybe that we don't have that. We don't have that solution now. If we did, then I would hear it. But on its own, this is not really. This is really definitely in the research side of the world. It's not really in the practical side of the world yet. I mean, I'm not
It's
sure what.
still, I think it's still like in terms of applications, I would say currently it's a bigger limitation of Monty that it can't generalize well than that it can't learn giant data sets
Okay,
of
Yeah, like or maybe another example would be like, let's say we want to recognize trees or we want to recognize cars. Right now in Monty, again, it's going to learn a car and it's going to learn a tree as like a flat
yeah,
model,
yeah.
and it's going to be really brittle as soon as the car changes its
Yeah, I
appearance.
got it.
It's not going to say,
I think like maybe I just have a different view of this whole thing. I mean, I continue to think, we talked, what's our chat GPT moment? What are we trying to do? We're trying to do, this amazing sensory motor robotic applications. And these kind of results are really important and essential, but they're so far from that the big picture we're trying to achieve that vast majority of people won't understand the connection. Machine researchers might. But to really get something broadly adopted, you have to sort of break out of the research community. You have to break into, implementers and stuff, who people are really trying to
um,
solve problems in the world.
I mean, yeah, I guess we could think about a more practical example. I think the trees and cars is actually a pretty good one to, yeah, basically show that Monty can learn a general model of cars and of trees and
Yeah, but
instead of individual models of each
that's
of
still
them.
far from an application. That's not an application. That's an inference problem.
but I mean, we're not
Um,
going to actually work on an application, but we want to make
yeah,
sure that an application we're kind of application ready. And I feel like
right.
we're maybe not
So
application ready
I
until we
right, great.
demonstrate that that works.
Great. I guess I'm saying these are all essential things we have to do. I don't think they're not going to significantly move the needle of people's, overall interest in Monty. It'll be in a narrow research community. That's how I feel about it. And we have to do them. So I'm not against this stuff. I think it's great. I'm just thinking like, oh, in terms of, again, writing a paper or demonstrating, I don't think any of this stuff is going to actually lead to some, a big new surge of people building applications on top of Monty. It's sort of like, yeah, you got to have this there. It's got to work. But it's not an
I don't
application.
know.
It's all
I think it would be exciting because like, yeah, take something like self-driving cars or different robotics applications. One of the things that's to my understanding of robotics is genuinely novel about thousand brain systems and is this idea that these 3D objects or whatever we're going to represent as a composition of other objects, and then that could give benefits to things like robustness. A lot of these systems still rely either it's a flat hierarchy, so okay, there's point clouds in the world, and maybe we recognize those point clouds, or they literally just use kind of deep learning systems, and it's like bounding boxes or segmentation
so,
maps or
if
whatever.
you could show this partnering with someone that's doing self-driving cars, how it improves self-driving cars, well, that'd be worth a lot.
Yeah, I mean, it
Right.
could be an interesting thing to explore because for self-driving cars, like you said, Niels, Monty could just replace the part that detects the objects and recognizes the different cars and trees and where they are relative to the car. But it doesn't have to do all the interaction part, the whole driving part of it. It can just plug into existing systems.
No.
And so we
But
don't need to
but
solve action generation before
so
this could
I don't
then.
know how many, I come with a bias from building products and trying to get people to buy my products and so on. And it sounds great. And it's correct, but getting someone who's building self-driving cars to even listen to you, this is it's going to be really challenging because they got so many other problems to solve. I mean, this could be one, but I'm just saying there's a huge gap between like, oh, we've shown this capability and someone saying, yeah, we're going to invest in this and put this into our system. You just can't underestimate that. So here we can come back and say, oh, we got more robust, object recognition, and researchers may be interested. But bringing it out into the real world is a huge step further forward than that. I think we're just all I'm arguing is about our thinking about how this is going to be perceived in the world. It's not about whether we should do this or not. It's not about whether it's important or not. I agree with everything you said there. I'm thinking like, I don't think the broader world will pay too much attention to some of this. It'll be pretty much in the research domain, which is
Yeah, I
okay,
mean,
but it
Yeah, I
just
mean,
no,
it
but
just
I think it's a good point. Yeah, and I think like with this one, for example, I think it's worth us remembering that Omniglot might be interesting to us, but yeah, maybe having other additional examples for a figure or for a result like this would be would be helpful to make the relevance to kind of application builders more obvious.
my guess is that if I were to take a swipe right now, my guess is that we won't really have this real hockey stick turn until we've shown some amazing robotics capability. And that will require all this stuff. So that's my guess. I can't
Yeah, I
prove
mean,
that.
even if like we don't have to aim for someone actually replacing their system in a self-driving car, but it might still be worth exploring a little bit. I mean, there are tons of data sets for self-driving cars out there that people are trying to improve accuracy on. Just for us to stay in touch with reality and actual applications, to just think through like how would Monty do on such a
I'm all
data
for that.
stream.
I'm all for that. I don't want to I just want to make sure that we don't take our eye off the broader goal. And so in terms of how much time we spend promoting these things, where it may not be too successful until later on. So I don't want to discourage any of this. I think it's all important, Mark. So
Yeah.
I just want to set expectations correctly. And as we talked earlier, how much time do we spend
Right.
on writing papers and getting them
Yeah,
accepted
or
and
I
things
mean,
like that.
because in the case of this one, getting all this stuff to work with Omniglot would actually be kind of non-trivial, whether or not we want it in a paper or not. We realized in the kind of September hackathon, because we talked about maybe working with Omniglot, and there's a few kind of challenges with that particular data set.
I forgot what Omniglot is. I remember you reached that conclusion. I guess I just don't remember Omnicon. I remember the term, but I don't remember what it was, why it was
Yeah,
difficult.
it's kind of this thing.
Oh, it requires sort of knowledge. I mean, now I remember it. When I looked at this, I said, oh, it really requires sort of an understanding of how strokes are written. It's not just an image. It's like you imagine writing these strokes. And that was sort of key to understanding the success. That was my conclusion.
Yeah. But yeah, there's weird things about it, like yeah, the data set is just a bit noisy, and yeah, anyways.
But even here, you see that different strokes are colored differently in that image. That's what I
Yeah,
remember.
but you see, like, for example, so I think the color represents the order in which they're drawn. So let's say red is 1, green is 2, and blue is 3. So a lot of them are written in that order, but partly because they're actually written by, like, just participants recruited on the internet rather than first language speakers of these languages. You can see someone here kind of did that one first, then that one, and then kind of
Yeah,
did
I
that,
I
didn't
wasn't even
finish
thinking
it, and then did that, and then still didn't finish it, and then it did another one.
right. To me, it wasn't the order in which they're written. It was the fact that I realized these are strokes, and I imagined myself drawing them as stroke, and not just like it's not just some sort of
Yeah,
two-dimensional image.
I
which
mean,
in that
we
data
could
is in the
simulate
data.
that with Monty. Like the dataset contains the order in which they like it contains the path, so we can make Monty move along that path basically. But
No, right.
yeah,
But when I saw it, I haven't written these things. So I just, when I look at it, I go, oh, that's a handwritten character. And I imagine someone, the pen and the physics of drawing the pen made a difference. Um, like if there's a T junction, I know that wasn't a single stroke because you can't draw a T with a single stroke, or a cross. It takes two strokes. Anyway, it's coming back to me now. That was you said it's a challenging one. But,
Right. So yeah, so that's that figure. And then, so yeah, I'd say, again, if this was a paper, these two would probably be the main results.
okay, just comment on that the figure there where you said this is the nonsense input. I
Yeah.
originally thought, oh, you really wanted to recognize that as an H. So in my prior was that you were trying to recognize letters. And therefore I said, okay, well, the H is the correct one then. That's the closest one you can get. But you saw that as, no, that's
Yeah, I
not
mean,
that at all.
maybe I didn't make the example extreme enough, but
No, but the point
yeah,
is I had a
I was just trying
prior,
to, I was basically trying to show that it's kind of a bag of features.
right.
Um,
My point was, is that you will, if I'm expecting to recognize a letter, then that would be the correct output. And yet, if I wasn't expecting to recognize a letter, then I shouldn't see it as an H. So it just tells you that prior expectation in the system actually determines which is the right answer.
yeah.
In that case, it wasn't
yeah, and
there
again, I
wasn't
don't
a
think we
simple
would
correct
need to
answer.
add nonsense input. I think it's just not possible to make the tolerances such that the accuracy goes up. It will just start confusing it with other letters.
Hmm.
Yeah. But yeah, and then this one I guess I briefly talked about before, but maybe that was before you joined the call, Jeff. But one kind of interesting sort of benefit of compositionality that we could highlight is how it can enable better model-based policies, which makes sense in terms of, again, obviously the world is hierarchical, the world is compositional, so the more we represent that in our learned models, the more our actions can be intelligent. But in terms of a concrete example in Monty today, it would be a pretty small change to get this to work, where so you have an object like this, again, with the flat Monty model, if it does its kind of existing hypothesis testing policy, where it's trying to distinguish, okay, am I looking at the TBP mug or am I looking at the Numenta mug? It doesn't have a good way of kind of finding where those models differ.
Right.
It could maybe look in kind of color space, but that has various issues. Whereas if this is a compositional model and it says, okay, well, at this part of my model, I have all these IDs for all these learn points for for logo A, and then in the other model, it's all these learn points for logo B. Well, okay, that's a very big difference between these two learned models. So that's the place I
Right.
should move to distinguish them.
Right.
Um,
I get that. Hey, you know what? Just looking at the title on this one, and I
Yeah.
was thinking like, oh, compositional models support better model-based policies. I immediately jumped to the thinking of, oh yeah, well, one of the compositional structures we've talked about is objects that the child objects are behavioral objects. You know, they're the dynamic behavioral objects,
Yeah.
and that would really be the better model-based policies. So like you're trying to achieve some result in the world,
Right.
and knowing that there are these dynamic components of an object and how to manipulate them. Um, that was
Right.
originally that's what that title suggests to me.
Right.
What what you're saying here is support better model-based policies for inference. and
Yeah. I mean,
you're right.
it may also, well, okay, maybe this wouldn't help with learning, but yeah, anyways. But yeah,
But it's not like it's
for like
it's not a
for
policy
changing the
for
world, kind of, right?
right.
Yeah, I see
It's
what you
not a
mean.
policy for manipulating anything. It's a policy for
Right.
just doing better, maybe better learning, but basically better inference.
Yeah, no, but I
Um,
see what you mean. Yeah.
I mean, that's, you know, just throw that out as another thing. That would be a pretty exciting paper where you combined the idea that there's these behavioral models and morphology models, and they both are, you know, and you can, and objects are compositional, including child objects of both of them. And so now you have all these behaviors that are inherited across objects. That's a pretty big idea. You know, so
Yeah.
I know we're not
Yeah.
there yet. We haven't
So
done
basically
that
what
yet,
you're
but
saying is, yeah, I
we're
feel like
gonna
what you're
do
saying
that
is an
this
exciting
year.
paper is all the cool features we're gonna have in maybe 6 to 12 months.
Right.
Yeah.
Okay. I mean, that's always been my fault, is I'm always looking out for the next big thing.
But I mean,
Um,
yeah, I mean, I think it's a fair
so
point and a use, yeah, like I think that's something like if we really did try and do a paper, that will almost certainly delay things by a few months in terms of
yeah.
implementing that kind of stuff. So yeah.
So, you know, just historically, the role I've played, even on building product design, I would always be most interested in building the product we don't have. You know, the next one that I know is going to be there. It's like, oh my God, it's going to be so much better than the one we've been working on. You know, but in the practical point of view, you have to balance those two things, right? You have to say, yeah, don't forget about that new one, but we still have to spend so much time on what we have here. So I'm just representing one end of the spectrum here. And
Right.
you got
But yeah,
some
but
of you
obviously
can,
we're lucky that we don't need to apply for another round of grants or something in 6 months. And so yeah, I guess we have the luxury of
we have a
not
choice.
having to do this paper.
Right. I wouldn't have done the capabilities paper, but you guys did it. It was great. You did it. I mean, so, you know, that's my fault. That's not that you shouldn't have done it. That's my limitations of my thinking. So it's the same thing here. I'm pushing one extreme, and you can just take what you want from it and maybe ignore it, or maybe you'll move a little bit towards the middle. I don't
Yeah. But yeah, I mean, that essentially concludes the stuff on this. I mean, again, if this was a paper, then I think somewhere in here we definitely want to figure this. Maybe this would be part of figure one, but you know, actually visualizing what these learned compositional models look like and things like that. I don't have any. Ironically, I don't have any visualizations of this visualization, but anyways,
yeah.
question.
Well, yeah, that would be
Yeah.
more. What would a visualization look like? What I think about is just like showing. I think of cortical hierarchy and showing where these representations are in the cortical hierarchy. But I don't know what would you do here. What would be a visualization?
Well, like an early start would be kind of the things that we showed at the September retreat. Let me see if I can find one.
Basically,
Yeah, here
what's
we go.
inside Monty's brain? Like, how do the learned models look like?
So
Where
like,
does
Yeah.
it store the
so, you
logo
know,
ID?
something like this, where it's like, this is of course a
But better.
bad compositional model, but where you
Just
know you
the-
have disk ID where you'd expect disk ID, and you'd have logo ID where you'd expect logo ID, and not kind of a shotgun of both.
Yeah, that's not an intuitive image.
Just things
Yeah.
like that.
Okay.
But you know,
right.
but then again, like this could be an interesting one to show for 2D on 2D objects like Omniglot, and 2D on 3D objects like logos on mugs, and then 3D on
Right.
3D objects like different scenes. Like it would just help people build an understanding of like, oh yeah, I can see how all those are compositional, and then now
Yeah.
I'm going to
Anyway.
see the results of like, what does that give us?
Even not knowing anything else, a representation like this is difficult for most people to understand. you don't look at that and go, oh yeah, I get it. You look at it and go, what the hell? All these buttons on.
I think
What
you
the hell's
would get
that
it
mean?
if it was correct.
Yeah,
Okay, maybe,
it's not.
maybe.
It's a work
All
in
right,
progress
I'm
example.
I'm playing devil's advocate here. I'm pushing back on all these things. So.
Yeah, sorry, Tristan, you were.
So it sounds like everything described here should do well on a hierarchical part decomposition benchmark, right? Like, and
Yeah, as in
there's
like where
plenty
it's
of.
explicitly decomposed, and also we have kind of some level of supervision of that.
Well, I mean, I don't know about the supervision bit, but like,
Well,
it seems
right now we're
like,
dependent on that, and I don't think we would be able. I doubt
well,
we
I'm
would be able to
saying,
remove that in kind of the time scale that we might want to.
gotcha. 'Cause talking with Jeff's combining behaviors, etc., like the behaviors should enable you to break up an object into its composites type of thing.
Yeah.
But okay. But
Yeah, I mean, we have different. I mean, yeah, like we already have some things that could potentially do that, like the constrained object models. And so, yeah, one thing we thought about again in the context of this paper is like we could revisit that and see if we could get kind of this more unsupervised decomposition. Um, but that's unproven, so it's like we'd firstly have to check that that works, and there'd probably be a lot of work to get that working. The data sets that are discussed here in general wouldn't require that. Omniglot might actually, because
But
because
not
yeah.
full supervision. We only supervise the parent object ID,
But
and I
but
guess
we kind
show the
of
child
we
object in
supervise like the
isolation.
experiment or like the learning, like we isolate this child object and then we present it and we say, okay, you're now learning an
Yeah, but
object.
only to learn the child object. Like once we show the parent object, we don't tell it where the child object exists.
Right. Yeah, so it's and that's like another one of the weird things about this again, like I didn't talk much about comparing to deep learning systems because I mean there's always the issue of like what architecture would we pick and all that kind of stuff and how much effort would we want to spend on that. But the other thing is just our training paradigm is so weird in a good way and a bad way. Like it would probably not work with deep learning at all because of catastrophic forgetting. Um, but people might also say it's kind of contrived and accuse us of having like, yeah. So, um,
how did deep
Can
learning come into this though? Because it's like we would just do well on hierarchical part decomposition. We would be like, you could still draw all those graphs on the hierarchical part decomposition, but without comparing it to deep learning, right?
yeah, I guess if we genuinely wanted, like, say we wanted to submit this to NeurIPS in May, I don't think there's any chance it would get accepted without comparisons to deep learning methods. Whether that's fair or not, I just think there's no way that anyone would
I
accept
mean,
it.
we could, if it would, we could, if we evaluate it on an existing benchmark like Omniglot, I don't think we would need to run the deep learning comparison, because other people try to beat that benchmark.
Sure. Yeah. But that would
Well,
be
you'd
an
have to.
easy one because like it also wouldn't be hard to get a deep learning um, comparison, but I think it'd be harder to like what would our deep learning comparison be for like logos on objects? Like I don't know. It would yeah.
I know. The research world just requires you do benchmarks. That's all that matters. Being a benchmark, but it's always been frustrating because I feel like there are capabilities that brains have that they don't have benchmarks for, and people don't test them, and yet you can't write about those because there's no benchmarks. It's like ridiculous. But along those lines, just in the interest of brainstorming, I thought one of the we had a couple of big ideas in the last year. How composition works is one of them, but the whole idea of behavioral models is a pretty big idea. And just the fact that they even exist and that, how simple they are. And that there's two types of models, and really it's just a twist in the input, and that's all the difference is. I don't, that would be, to me, if I was reading papers, I would go like, oh shit, that's an amazing idea. You know, um, because no one ever thought of it before. Like that. I don't think anyone. I don't know. I don't know what the world of machine learning thinks about behavioral models like that. I don't know what,
I feel like I need a recording of you from like 12 to 6 months ago when we were
Right.
still finalizing the hierarchy paper, and compositionality was still exciting and new.
Well, it was
No,
exciting to me
I'm
it's
joking, but
exciting to me to solve the problem. Right.
yeah,
That was exciting. I'm not sure it's exciting to other people.
yeah,
Anyway,
okay.
again, this is not a replacement for compositionality. I said in the favor of brainstorming.
Yeah,
I just threw out just something else to think about.
right.
Yeah, I think, I think the compositionality, it seems to me that people have understood for a long time that the world is compositional to some extent. I mean, philosophers would understand this. It's almost intuitive. The challenge for us was, how the hell does the brain understand that thing? How do you model it? How do you create models and learn it? That to me was the challenge, and it was really exciting to figure out how that worked. I don't.
Yeah.
I feel when it comes to like behavioral models, that was something that I certainly didn't anticipate and had no idea, and that's like a whole new idea to me. I don't know if that's true in the machine learning world in general, but anyway, for me that was like a whole new idea. It's like, do people even model behaviors? How do they do it in machine learning?
I mean, often it's kind of in the it's often kind of modality or task based, I feel. So it's like, there's lots of models that predict frames in videos. And so the idea there is, or frames in video games. And so the idea there is it would kind of predict the
Mm,
behavior of kind of in the sort of natural physics of the world. Um,
right, but
I think
those are the
I think the evidence generally points to the deep learning does like a really good job of sort of approximating that and looking like it's doing a good job in sort of image space,
right.
but without actually learning the kind of
Without
representations
knowing,
we have.
have no real
Like
idea. Well,
like the
yeah,
classic
you're right.
example is like object permanence, that you have like a bunch of you have like two
Right.
puppies in a video, and then suddenly like 10
Yeah.
puppies like spawn out of it. Um, but it's
Yeah.
like photorealistic. Um,
Right.
and yeah.
Well, it's interesting because our whole world was built around structured models based on reference frames, and which is pretty unique, and maybe completely unique. I don't know, but certainly not many people do that. Um, and then the idea within that world that the same model could be applied to behavioral models is pretty damn cool. Now, if you're not thinking about structured models like we do, and you're just thinking about, oh yeah, we're going to, do video predictions, whatever, then maybe it's not, behavioral models aren't as cool. I don't know. I'm just speaking out loud, just thinking about loud. What I think I find interesting, and maybe that other people might find it interesting too.
Yeah.
Um,
Oh, I
No,
guess
I mean, I
a
think, yeah.
behavior model, like real quick. I mean, I was gonna share this on Slack, but I think in deep learning, Feifei just released like a behavior 1000 data set. Again, it's kind of more like video related, but let me see if I share it.
yeah, I imagine it would be.
Like something like that. There's some
This is probably using the word behavior in kind of the more traditional sense of like
right. So it's
a
kind of like
human or a robot's behavior, right?
yeah,
Right,
yeah. It's like a
right,
simulated environment. It's like okay, you get some instruction, like turn on the radio receiver, and then I guess there's some video about like
right,
that
right,
it can
right.
kind of look around and
I
it
mean,
wants to
this is my
I
point.
don't
I
know.
think the idea that what we've been using the term behavioral model for objects, or is it's really elegant and novel. I don't know if we can convince people that, but it's
I mean,
really
I
kind
think
of
you're right. I think yeah, I think there's for many decades there's been this concept of like intuitive physics, but I think talking about just how general that it's not just about physics. It's just that everything from an iPad app to whatever has
yeah.
kind of behaviors. I
Yeah.
think that at
And
least
even humans.
I'm not
I think
familiar of like a
it's
conceptual description
right,
that kind of similar to that.
right, and of course it's really beautiful because it fits within the Thousand Brains framework. But you have to appreciate that first before you realize
Yeah,
how nice it
that
is.
might be lost. I think
Yeah.
I think people getting excited about it also using reference frames may be lower on the
Right. Right.
actual whatever.
Oh, at some point,
But
people
yeah,
will
if it could
people will wake up to.
powerful, cool things like power a robot demo or whatever it is, and yeah.
Yeah. Right. I mean, part of our job is not just to show we can do better things; it's to educate people about the whole way of thinking about this. You know, we spend a lot of time on that. Will does. We all do. And that will pay off eventually.